Good evening, ladies and gentlemen, and thank you very much for coming along tonight to listen to my presentation. I first got involved with the LHDs in September 2015 when I was asked to come along and support in problems to do with warranty claims. And that was the beginning of a 6-year journey, actually, so it's been an interesting time. So the LHDs, they entered service in 2014, which was first HMAS Canberra, and then in 2015, which was HMAS Adelaide. Both ships had a number of significant problems relating to the propulsion system. And this presentation will cover these issues. I'm going to go through the background and nature of the problems that were propulsion and propulsion related, the investigations that centered around the events of 2017, key findings of the investigations, the solution to the problems, the implementation of the solutions, and then we'll talk about HMAS Canberra's sea trials in 2021, where we actually proved that the solutions were effective. Okay, so the vessels themselves, vessel particulars, overall length is about 230 meters and 207 at the waterline. The beam is 32 and a displacement of 27,400 tons at a nominal draft of 7 meters. Okay, this is an all-electric ship. The power plant consists of 2 man diesel-driven generator sets, each rated at 7.45 megawatts, and 1 General Electric LM2500 gas turbine-driven generator rated at 22 megawatts. The actual propulsion itself is provided by 2 Siemens Shottel propulsors known as SSP-10s in their original configuration, and they have an input power of 11 megawatts. These pods have now been renamed by Siemens as SI Navy SI pod. The pod arrangement. The pod arrangement consists of 2 major elements. There's the azimuth module, and this pod can rotate through a full 360 degrees, and then the propulsion module at the bottom. The steering gear plate, so this part up here, the upper part, this is bolted securely to the deck in the ship. This part doesn't rotate, but everything below here, the cone, the stem, and the motor unit all rotate together. The motor at the bottom in this section here is double-ended with a forward propeller and an after propeller. And the total mass of this is about 170 tons, with the motor itself being 98. Okay, the scope of the presentation. I'm going to deal with the problems affecting the performance of the 2 LHDs, and they were profound and often complex and interrelated. So there were 2 aspects of the issues we had to deal with them being new vessels. One was the technical issues, and the second was the commercial. And to deliver an effective technical solution, you have to deal with the commercial terms. However, this presentation will only look at the technical aspects. The presentation itself is unclassified, and therefore there are no pictures of the 3-bladed original propellers or the 4-bladed new propellers. That's very unfortunate, but that's the way Navy wants to pay. Okay, the background to the problem. So complicated, lots of problems with the propulsion, and we could divide them into a number of key areas. So the first one that came up, and this was before the ships were delivered, is we had problems with the corrosion. And the first issue was the blade nuts were corroding. So the 3-bladed propellers were bolted on with stainless steel nuts, and they started to corrode very severely, and they were replaced with duplex stainless steel. We then found that the propeller blades and the hubs started corroding. Understand the problem. They then suffered from excessive water leakage and oil leakage into the pod bilges. So inside the pods themselves, you cannot access these when they're afloat. They have bilges at each end with pumps which pump the contents up, and there was a real problem with the seal issues which we had to deal with. We also had cavitation erosion of the propeller blades, and the ship's staff complained frequently about the high vibration levels. Now, the ships have been delivered with CPAC-2 notation, which is crew and embarked personnel accommodation comfort, and the numeral 2 is the level that class gives to it. However, when I went back and reviewed this, the CPAC-2 measurements hadn't really been done correctly, and they were non-compliant with the LR rule requirements. the high level of vibrations were definitely being caused by cavitation. And this was also consistent with the blade erosion we were seeing at the time. So we had to undertake a set of extensive investigations, and this was really started in 2017 when we formed the Transition and Remediation Program. And on the propulsion side, we had to look at the propeller blade cavitation and erosion, corrosion issues with the propellers, pod equipment issues. So this was stuff within the pod itself that was causing us some problems. So in the investigations, there are a number of key players. So obviously there was the Transition and Remediation Project, but then within the Commonwealth, we utilised the Naval Technical Bureau, which is now known as the Directorate of Naval Engineering, Defence and Science Technology Group, DST, the LHD System Programme Office personnel, and we also contracted out to a number of external agencies, including Lloyd's Registered Technical Investigation Department, TID. Industry's input, this was from two main elements. There was the ship designer and system integrator, Novantia, and the pod OEM, Siemens. The initial investigations began in 2017. So as I said, we'd started to see these issues, and NTB and DST got involved to look at the corrosion of the propeller blades. So we'd had divers down, we could see problems with cavitation, erosion, and also corrosion. And one of the key things there was the ICCP was not functioning as it should have done. The vibrations, now we knew we had problems with vibrations in the ship, and in 2016 we contracted TID to come and do measurements, but unfortunately we were unable to get sufficient ship's time to do any measurements at that time. But that all changed in March 2017, and within 24 hours actually, we had HMS Canberra, where the problems with water and oil coming into the bilges was such an extent that her pod had to be locked, and she had to return to Fleet Base East. And 24 hours later, routine oil sample came back showing we had high bearing oil, iron content in the bearing oil on the port pod, and she had to return to Sydney as well. This caused a few ruffled feathers, and suddenly people started listening. So consequently, in April of 17, we formed the Transition and Remediation Project, and this had to look at the remediating the LHD material problems, not just the propulsion issues, but a whole load of other problems. Okay, so what we did in 2017 is we docked both of the ships. First, we did it HMS Adelaide in May and June 2017, because she was in the worst physical condition. And then we did Canberra in the September and October. And the purpose of these dockings was to return each pod back to its baseline condition. So we replaced seals and bearings and everything else, give it a full 5-year overhaul. And because of the condition of the propeller blades, we put a complete new suite of 3-bladed propellers on each pod, on each platform. Just to show you give you some idea of the problems, the extent of the issues we had. Here are 2 pictures of Adelaide's propellers from the 2017 docking. So at this point in time, she'd only been in service for about 19 months. The top picture here, it shows tip vortex cavitation and also corrosion. And I mean, this is severe cavitation erosion, and the corrosion shouldn't be there at all, of course. And then the lower picture, what we see in this area here is corrosion under a stable cavitation sheet. Now we had LRTID came to investigate this, and their hydrodynamicist said that they'd actually had evidence, or they'd seen what they thought where when you get a sheet cavitation, you get an oxygen-rich environment, and that encourages corrosion if the other problems are there as well. So that's a very extreme case, really, where we were losing huge amounts of material through cavitation and corrosion, and one was feeding the other, and we were losing our propellers. Okay, so we then returned both ships to normal, and then we then went back to sea to really investigate what was causing these issues. So we had the recommissioned pods to overhaul. So that was to take them through a series of 6 different tests to make sure they could perform as they could in terms of propulsion and steering. We then carried out a number of vibrations, structural vibration measurements, and this was split into 2. The first was the empirical modal analysis, which was done alongside to determine the natural frequencies of the hull, And then the second was to measure the structural response to the hull while underway. And then we were going to assess the vibrations in the ship against the requirements of CPAC 2, but for vibration only, not noise. To also give us a lot more detail on this, we put holes in the bottom of the hull, and we mounted hull pressure transducers above the forward and after propellers. And we also put observation ports in so that we could put a borescope through at a number of key positions to observe the performance of the propellers throughout the speed range and in various maneuvering positions. We also conducted local vibration of the ship structure and equipment as required. We did some serious measurement, particularly by DST and DNE on the ICCP and the hull potential problems. And then on top of that, we had another multiple set of trials and tests across auxiliary equipment and the such like on the ship. And when we went to trials on Adelaide in July 17, we had, I think, 45 people in the trials team altogether. So fairly extensive and a lot of work. Once we'd done Adelaide's trials, we got the initial results. We then refined those so that we could look at more stuff on Canberra, which we did in November 2017, particularly the switchboards and the masts. This is the layout we did for the propeller observations. So in the middle here is a schematic of the pod on its side, of course. And this is the head box above each of the propellers. This is starboard side, port side, and on HMS Canberra, which was the second ship, we did more observations and more measurements. What we have is a number of pressure transducers, P1, P2, P3, and P4. They're above the forward and after blades. And they also corresponded with some tank testing that Marion had done previously. So this was a deliberate position of those transducers. We then put vibration transducers at various places above the port and starboard pods. And then we put in borescope holes. So we had a total of 3 on port, 1 here, then B2, B3, and then equivalent over on the starboard side, B5 and B4. So this is where we could put the borescopes in and observe the performance of the propellers while underway. Okay, the results. So in terms of the structural vibrations, the modal analysis showed us that the flight deck and superstructure mode identified as 7.4 hertz equal to the prop first blade rate, and I'll talk about that a lot, at 148 RPM, characterized by a rolling motion of the superstructure and the flight deck. And the proposed solution for this was to reduce the propeller pressures exciting the hull. 2-deck modes were identified at 7.6 hertz and 8.3 hertz, equal to first blade rates of 152 RPM and 166 respectively. The solution for this was to strengthen 2-deck and reduce the propeller pressures impinging on the hull. The aftermast was found to have 2 local modes at 5.9 and 6.8 hertz with vibration amplitudes which exceeded mil standard 167 TAC1 for electronic equipment. And the solution for this was local structural modifications and once again to reduce the propeller hull pressures. The hull pressures themselves, we measured these, and the max was just above 5 kilopascals, 0 to peak, at close to MCR, maximum continuous rating. Vessels of this size, we can compare this to a ro-ro, we would normally expect the hull pressures to be in the region of 2 to 4 kilopascals. And the excitation force for this was the first blade rate of the propellers, and that was the dominant source of the vibration. This is an example from TID's report, which shows the nodes which appear on 2-deck. The top one is for 77.6 hertz. And there you can see, particularly around the senior sailors' dining room and the embarked forces dining room, real peaks, which are very uncomfortable for them at certain speeds at 7.6 hertz. Then the second one shows the higher frequency of 8.3 hertz. And the one that's really suffering here is the hospital. And this hospital does have an intensive care unit in it. So not particularly good for anybody not feeling well. And again, the embarked forces cafeteria got hit at this frequency. So we have these natural frequencies on 2 deck, which were being excited heavily by the propulsion system. Okay, CPAC2 we measured, and this was only for vibration and not noise, and I had 52 compartments above the CPAC2 limits, 40 of which of the 52 were actually on 2 deck. And of course, this is the biggest deck in terms of administration, accommodation, and crew comfort. The PCRF, which is the principal care reception facility or the hospital, that was particularly badly affected, and we had a number of residences below the main one at 8.3, where everything in there was shaking pretty badly, especially the beds. And as we see there, exceedances could be expected to occur at lower speeds than 85% MCR, which is the power setting we required to do the CPAC2 readings. And as I already said, the hospital was a bit of a mess. Okay, the pods. So this is now looking at the way ahead. So in 2018, we'd gathered all our data, we'd done a lot of analysis and come to some firm conclusions about our problems. But one of the things we decided was we had to get new pods. So we had 2 ships, 2 pods on each ship, but no spares. And if we lost a pod through a total failure, the repair time to procure a new pod was a 2-year waiting list. So we decided that was unacceptable. Also, if we looked at midlife refit, the time required for a motor overhaul at that time, whenever it may be in the future, would result in an unacceptably long docking maintenance period. Now, and then that's the last part of the note, is that the main driver for this is the material which is used to make the permanent magnets in the motor, which comes from Russia. And this was before Ukraine came along. So it was a good move at the time, and we have 2 spare pods now. Okay, the structural vibration problems. These are complex and multifaceted. So having done the investigations in the sea trials on both ships in 2017, Navantia then went to Juan Carlos, which was the base ship for the Spanish Navy, and they did some EMA, experimental modal analysis, on the pods in dry dock, and they found there's a natural frequency of 7.5 hertz, which is 156 RPM, very close to those natural frequency ranges we were getting on 2 deck and up on the flight deck and in the superstructure. They also estimated that the thrust variations, this is the variations between the forward and after propellers, was in the region of 4% across the propeller blades. And then, of course, we had the erosive cavitation and excessive hull pressures that were the dominant excitation forces on the hull. So we had 2 potential solutions to come out of this: was redesign the propellers and or stiffen the platform to do structural changes. Propeller redesign. This was the one we chose. Although it was the simplest and the cheapest option, it was neither simple nor cheap. And then the advantage of going to more blades is each propeller blade will see less thrust. It'll improve the weight flow from the forward propeller onto the after propeller. And what happens is you lower the speed and therefore the power at which the natural frequency occurs. So instead of occurring at 156 RPM with a 3-bladed, with a 4-bladed, it'll come down to 117. And as we've got a square of the power, it's a much lower excitation force. So we went for that option. Okay, what we then did using propeller observations and the hull pressure data we'd collected during the sea trials in 2017, and we used Canberra's data from the November trials, basically because the weather had been much better and we had better camera film of the propellers. And so we took that information and then we went to Marin. Now, Marin, at the request of Navantia and Siemens, had done some work on the propeller design prior to delivery of the LHDs, and they'd modified the after propeller. So Marin actually had a model hull and models of the pods with propellers still in the Netherlands. So what we did was we gave them the information, the video and the hull pressure data, and provided it to them to tank test. And they reran the earlier tank tests they'd done with the original 3-bladed propeller designs, which we had on the pods. And they adjusted the scale and model coefficients in the tanks to replicate what we'd seen at sea. So to get the same levels of cavitation, pressure on the hull, et cetera, et cetera. So what we ended up with was a real good idea of that what we had in the tank could be replicated at sea. And this would, in the full scale, and this would actually then inform our redesign procedure. Also in early 2019, Maritime conducted a particle image velocimetry, PIV, much easier to say, testing, and CFD modeling to determine the wake field characteristics of the rear of the pod. So this is behind the rotating forward propeller. This is where the wake field comes into the after prop. And we share this information with Siemens and Navantia to inform the redesign. So this is the setup that Maritime used. So this is the original 3-bladed propeller design on the forward end. And they took off the propeller, and then the green line here indicates the measurement plane which they did for the PIV system. And this is all done using lasers and very clever stuff in their tanks. From that, they then produced this, this wake field. So you can see here at the forward end, this is the forward propeller. And this propeller rotates inboard over the top. So this is a starboard pod. So it's actually rotating, the forward propeller is actually rotating from right to left. It's going anti-clockwise. And this shows the 30-degree intervals, the changes in wake field that the after propeller will see coming onto it. And what really stands out, and I'll come out more in the next slide, is the complex form in this area here, and it's very intense. And that's maintained, and also the effect of the fins, which are on the side of the pod. So this was the analysis they did on that to the wake field. So this is now looking, orientation-wise, is looking from forward to aft. So on the left-hand side, we have the wake field for the forward propeller. So this was the flow that it sees on this nice, clean wake field coming in, with some interaction boundary layer with the ship. And then this is the wake field that the after propeller sees. And the real complex area is this area here immediately behind the stem and at the rear of the pod. So we have very low velocities here, high velocities here, and obviously that causes a lot of pressure differences. So this was the complex wake field that the propeller designers had to deal with. Okay, so then in May 2019, the Commonwealth contracted Navantia as the ship designer and integrator to manage the study for a 4-bladed propeller design. And we had a number of propeller design specifications. So the principal one, of course, was the original general design criteria, like power, speed, etc. And then we put some additional ones on top based on the information we had found during the investigation. So we needed to ensure we had low shaft excitation forces. This is in the pod motor itself. We need to prevent cavitation erosion, reduce the vibration caused by cavitation, maintain the efficiency, have a delayed cavitation inception speed. I raise the cavitation inception speed, prevention of inboard propeller noise, and then reduce the pressure, the hull pressures from 5 kPa down to the range of 2 to 4 kPa. So the original intent had been for Siemens to work with Maritime to redesign the propellers. However, Siemens came up, they're very conservative, and they came up and they said, we don't want to do a 4-bladed, we want to do a 3-bladed again. So we agreed to that, although we were not convinced it was the right way to go. And Siemens teamed up with SVA Potsdam, stateside of Berlin, to design another 3-bladed, and this is going to be Mark V on the back end. Then Maritime worked with Navantia to come up with a 4-bladed design. And as part of the contract, we as the Commonwealth asked Navantia to review both designs and provide us with their opinion, what would be the optimal design to resolve our problems. At the same time, Siemens had reservations about the motor shaft dynamic performance, and in particular the lateral vibrations. And they did some calculations which showed the 6mm air gap in the motor would close with a 4-bladed propeller. We were not happy about this. In fact, we didn't really believe it. So we then asked Siemens to justify their results, and they couldn't. So it's actually, I should perhaps say here that the original pod was designed So the double-ended pod, the theory behind that was done by Chattel, and Siemens then came and put the motor in the middle. What happened a number of years ago is basically went through a divorce. So the IP around the actual design of the propellers and the azimuth unit and everything else went out the door. So Siemens great at building electric motors and everything else, but that knowledge wasn't there. So we had a bit of a dilemma. And we actually did a separate study, which I'll talk about in a moment. So this is the design that SVA Potsdam came up with. And it was a 3-blade design at Siemens' request. And it consisted of 2 highly skewed propellers, forward and aft, each with an angle of 37 degrees. And what they also did was they changed the fin design here. Now, part of our original specification was to retain the original fins, because it's another complexity and more cost, et cetera, so it didn't meet our requirements there. The Maritime 4-bladed propeller, unfortunately, I cannot show you the design. So that came out as a monoblock design, and this was constrained by the fact that the hub still has to maintain the original fundamental dimensions. This because it has to sit on the shaft and be of a certain size and geometry to be able to meet the requirements of the loads it's going to take in service. Benefit, much cleaner lines, and remove the bolted securing arrangements of the blade, which contributed significantly to cavitation at the roots and around the hub. Disadvantage, of course, if you damage one blade, you've got to change the whole propeller. And the forward prop is skewed, and the after one is highly skewed. The forward and after hub caps are different in length and form. So this is the Marin model, which goes back to the original design before the LHDs were delivered. This is the port side, and there we can see they have a standard sort of module there, which just provides a force. And then at the bottom picture here, this is the model of the SVA Potsdam 3-bladed design set up for the tests. Okay, the model tank testing of the new propeller designs, there was a number of different tests undertaken. There were the open water tests with the pod model towed along the tank without the model hull. And this was to determine the loading of the forward and after propellers and open water efficiency. Propulsion tests with the model hull. This was to determine the power and shaft RPM of each design, and runs were done at 100% and 80% MCR. Cavitation tests and open water. This was to provide cavitation observations carried out in various conditions. The pod model was towed along the tank without the model hull. So the summary of the results which came out of the tank testing, the propulsion test, the speed and power performance of both designs, so that was a new 3-bladed plus the 4-bladed, were almost identical. Cavitation test, the 3-bladed, that showed erosive cavitation on both front and rear blades. The 4-bladed propeller had no erosive cavitation. There was some root cavitation on the rear blades, and that was eliminated by doing a minor redesign. Hull pressure fluctuations. The 4-bladed was lower than the 3-bladed, and the 3-bladed had higher harmonics with amplitudes greater than 1 kilopascal. The total hull excitation force, FZ, in the vertical direction, the 4-bladed was 50% less than the 3-bladed. Okay, so this is some still shots from Marin's tank testing, and this is for the new 3-bladed design. So we can see here's the forward propeller, the after propeller, and the forward propeller you can see at the top here, there's a tip vortex, and at the aft end you can see the same there. And just to see if you can remember the size of those tip vortexes. This was analysed as showing the tip vortex cavitation, which was stable, but also there was sheet cavitation, which was determined to be erosive. And there was some sheet cavitation also seen at the root. This is the 4-bladed design. Yes, we've got them blanked out, I'm afraid, but that was the rules. There's no tip vortex cavitation on the forward blades, which is observed. And if you look, you can just see a very fine, small element on the after blades there. And it shows in this one that tip vortic cavitation is stable and a little bit of sheet cavitation at the root. And so Marin did a redesign to eliminate that. Okay, the other big issue, of course, was the shaft, the pod shaft vibration analysis. This is actually the dynamic performance of the shaft. So we have the motor in the middle, and on each end of the motor there's a shaft, and then on the end of the shaft is the propeller. So this is a fairly substantial rotating mass, and Siemens were concerned that this was going to cause problems with four-bladed propellers. So as I mentioned earlier, Siemens were concerned, and they said that they thought the air gap would close and the level of vibrations would be unacceptable. And we were not convinced about that. So, and also they didn't agree with Marin's methodology for determining the propeller forces. And Marin's got considerable experience in doing this. So there was some contention, and we as the Commonwealth didn't agree with Siemens. However, they are the pod OEM, so we had to actually come up with a solution and do a sufficient analysis and investigation to prove to ourselves, to all of us, all the stakeholders, that actually four-bladed propellers would not be a problem. Just to put a little bit of context on it, the original three-bladed propellers were essentially the same mass. The four-bladed propellers, the forward one is about 12.5 tons, and the after one is 14.5 tons. So there is a difference. There are changes. Anyway, so what we did then, the Commonwealth through Levantia, we contracted LRTID in Southampton, to conduct shafting vibratory analysis using the input data from both Marin and Siemens. And then they conducted extensive modeling on our behalf. So this shows the basic model that they used with the motor in the middle. This is the forward propeller, the pull propeller, thrust bearing, compact aligning radial bearing, and then compact aligning radial bearing, thrust bearing, and the after propeller, which is a push. So that was their fundamental model. And that's how it looks like in the finite element model. So there's our motor, two shafts, and the propellers at each end. Now the shafts themselves have a number, 20 actually, notches. And this was a concern that we would get fatigue cracking in those notches. And that was really the whole point of this analysis, to prove that either it would or wouldn't. So TID did it was a significant amount of analysis, but using both Marin and Siemens data. And the results of it can maybe summarized as following. So the axial vibrations at 1 times and 2 times the blade rate were unlikely to cause concern. Torsional vibrations, extensive model scenarios completed, including maneuvering. Results indicate that torsional vibrations were unlikely to cause a problem. Lateral vibrations, the max half-range vibratory lateral direct stress evaluated by force-damped analysis across 14 operating maneuvers was 25.74 megapascals. And this was unlikely to cause a concern as well. So then we have the high cycle fatigue combined with torsional and reverse vibration. High cycle fatigue safety factors for 10 to the 10 cycles, including torsional and bending stress concentration assessed against the DNV guidelines, which are very comprehensive. This came up with a safety factor of 4.75 and was deemed not to be a cause of concern. The total stress and low cycle fatigue combined torsional and reverse bending for notch shaft locations, the safety factor was calculated at 4.63, indicating yield reversals were unlikely to occur. And then finally, the electric motor air gap. The minimum safety factor on the electric motor air gap of 3.28 millimeters was 28.8 and 3.6 for vibratory and total lateral shaft displacement, respectively. This meant that even in the worst conditions, the air gap was always 3.6 times larger than the actual radial movement of the rotor, and therefore we would never compromise the electric motor air gap. So the conclusion was that the Marin four-blade propellers and the vibratory response were acceptable. So the design selection, conclusions, the SVA three-bladed propellers fulfilled the Commonwealth's requirements except erosive cavitation. Hull pressure fluctuations at second and third order, blade passing frequency considered too high, and therefore is not a valid option without further modifications. And the other thing that put us off, we'd already had 4 iterations of these propellers, particularly the after one. The Marine 4-bladed propeller fulfilled all of the Commonwealth's requirements, noting they had the potential to reduce thrust fluctuations by 77%, the original 3-bladed propellers at 7.8 hertz, whereas the SVA 3-bladed propellers had the potential for a 32% reduction. The vibratory analysis indicated the performance of the 4-bladed propellers would be satisfactory. The COA, our decision was that we would go with the 4-bladed propeller, and that was after further discussions with Siemens, because obviously as the OEM, we had to have them on board. So that was our decision. Now, just before I move on to the next part, so in 2021, we put Adelaide back in. So you saw Adelaide's propellers earlier, so they were badly corroded, and they were also very badly eroded from cavitation. This is the brand new propellers 4 years later. What we see here, as you see that we've still got really bad cavitation damage, particularly from the transition to the leading to trailing edge. And then on the bottom right here, you can see the extensive pitting on the blade face. So, but what we don't have is corrosion. So we got rid of the corrosion, but we didn't get rid of the erosion. So we had to change these. I mean, propellers should last the life of the ship. So one thing we did do in 2017, we did eliminate the corrosion, although the potential difference between the shaft, the pod, and the hull was still outside of accepted limits. But that was one good point. But anyway, still this terrible damage which we had to correct. Okay, the 4-blade propellers. So having gone through the design process, we then had to get them, and we contracted Navantia Australia to do this work. So they were required to produce the manufacturing. So the drawings, the design's one thing, but then you've got to get through to manufacturing drawings, class approval, and what have you. So they produced the manufacturing drawings, and NTB, they reviewed the drawings on behalf of the Commonwealth, and then Navantia put them through LR, and they were reviewed against the design rules which were in force at the time under the Naval Ship Rules, January 2019. The requirement was to procure 3 sets of the 4-bladed propellers, with the delivery of the first set in time for Canberra's planned docking in September 2020. To identify a suitable propeller manufacturer capable of meeting all of the requirements, and if possible to utilize Australian industry. The manufacturing criteria was for the propellers is the standard ISO standard 484 TAC 1, shipbuilding, ship screw propellers, manufacturing tolerances, propeller diameter greater than 2.5 meters. Tendering. So Navantia went out to 3 Australian companies and 6 international ones, and it covered Asia, Europe, and the USA. We then did a joint evaluation of the tender responses with Navantia. Unfortunately, Australian industry was unable to cast a propeller of this size. So the after one, which is 4.5 ton, 14.5 tons when it's finished, needs a mold of 20 tons, and couldn't do it. And also price-wise, they were very uncompetitive. Not all the international suppliers responded. And then we had the successful manufacturer did provide a complete tender response and was able to meet all of the requirements and our very tight schedule. So this was around about February 2020, and we were needing the propellers here in country by no later than beginning of September. So it was a pretty tall order. Okay, so we did, so again, we used Navantia to procure the propellers on behalf of the Commonwealth, 3 ship sets. And the propeller manufacturer, and this is the time that COVID came in, of course, so we couldn't go anywhere, and nor could anybody else. The quality assurance was a very important factor in this. So the local LR office and surveyors, they provided the LR class rule materials surveying and inspections, and the propeller manufacturer about every fortnight send us a very detailed update on the progress of all 3 ship sets. And it's important to note that actually all 4 propellers are different. So the forward ones are basically the same, but they rotate in different directions. And likewise with the after ones. And also the hubcaps, the forward ones are the same and the after ones are the same, but the forward and after different. So here we have some this is just an example of some of the stuff we were sent. So here's the propeller mold being formed with the sand and the cores, etc. Pouring the mold, and then a very important one, of course, is the fit up of the taper to the propeller hub. The dummy taper, this was actually provided by Siemens, and as you can see, there's it going in all blued. There's the result inside the hub, and then there's the taper when it came out. And when we actually fitted them, they all fitted very well. It was a very good job, very high quality, and I say impressive, and they met our delivery dates. So having completed that, so Canberra was the first ship to go in September, October 20, and she came out, and then we did sea trials in March 2021. And the purpose of the sea trials there was a number of purposes. Right, we had to recommission the propulsion plant, and we'd also fitted the new pods. So 2 new pods had arrived, and they'd gone on to Canberra, and we took the old ones off. And to commission them, there were 6 phases to that. Then we did a vibration survey, propeller observations, CPAC2 noise and vibration measurements to determine the effectiveness of the new pods. And then to do the sea trials, we needed quite tight environmental conditions. So we had to have sea state 3 or less, depth of water at least 5 times the nominal draft of 7 meters. And we needed to keep the helm at a minimum of 5 degrees, maximum of 5 degrees during these steady trials. Then we did a number of other propulsion trials, pod run up and heat runs, steering trials, and crash stop. Okay, the results. So the structural vibration survey. So that's to reevaluate the structural response of the platform at the same locations we measured in 2017. So you've got to measure in the same place both times, otherwise you can't really gauge the effectiveness of your solution. And also we looked at the background environmental levels of vibration in the magazines and the Nolka launchers on the ship. This was an outstanding requirement from build. So actually to do the trials, the requirements were pretty tight, and we had to install vibration transducers once again at key locations in the ship, and we used the same locations as we did the first time round. But because we were doing a lot more places and we were doing the magazines, we had to do 3 setups, which took 3 days of trials, each for about 10 hours. At the same time, we had the hull pressure transducers installed, and we took borescope observations, again, exactly the same places and at the same speeds. For the dynamic measurements, we did the run up and run downs for the operational speed range, because there is an overpower on these as well. And we recorded each of these in 2 RPM steps for 2 minutes, so extensive trials. And likewise, we did it on the run down, but in slightly larger RPM steps of 3 RPM. Okay, this is to illustrate the extent of how we have to instrument the ship to conduct the vibration measurements. So this is looking forward. So this is the port pod, starboard pod. So the port pod, where we had the majority of our instrumentation. So this was the hull pressure measurements, the borescope, the majority of the borescope. So this was our control point, where the TID set up and ran all their trials from there. Then we have to have a link across to the starboard pod, because the pods are synced, so we could make sure the pods remain in sync, etc., and our measurements. And then from there, we ran cables through the ship. And this is an example here of 2 deck, where there's 15 vibration transducers at these locations, and each one of those is triaxial, so it's measuring the vibrations in the 3 orthogonal directions. And we did up to 32 transducers in a particular trial, so we're looking at about 66 data channels minimum. And then we had to go all the way up to the top of the ship to do the mass, and we reckon we had somewhere in the region of 5 kilometers of cable run out to do this. It's a big ship, it's a big job, and it needs to be done by people who really know what they're doing and are very well organized. And it was a fantastic exercise, actually. For the observation program, we did very similar to before, and we looked, observed it from the 2 locations, mainly B1 and B3 on the port side. And also we did some maneuvering trials to see how the cavitation or the performance of the propellers was under small angles. And we did this at 0, 6, and 10 degrees of helm at speeds of 90, 115, 140, and 160 RPM plus maximum. And again, we did these observations from B1, B3, and B1, B2, and then B4 and B5, looking at different things. And I'll show you in a minute there's some of the snapshots we got. This was quite extensive. It took 10 hours to do. We had to do it in good sea conditions. It was lucky the sun shone. We had to do it with the sun coming in on the port side of the ship predominantly, because you don't natural light only for these observations. So lots of coordination with the bridge and the control room and with the trials team. Okay, to do the CPAC2 measurements, this is on a ship of this size. There's 1,100 compartments on the LHD thereabouts altogether, and for the requirements and the rules, so we developed a plan, a measurement plan, which had to go through LR for approval, and we needed to measure 500 compartments, and we were going to do the trials at 90% MCR. To do this, we had 3 measurement teams. And accompanied by ship staff for guidance and also to get into compartments, so security compartments, et cetera, and we actually managed to get it done in one day. They worked really hard, and that was a 14-hour day to do those 500 compartments or so. And that was doing vibration and noise, and we're having to maintain the ship at 90% MCR. So it's a big coordination job. We then did CPAC2 Harbour, but we actually did this at anchor, which is allowed in terms of the class rules. And this was normal harbour condition with diesels running or whatever and auxiliary equipment. A lot less compartments to do, thank goodness. But we needed to measure also when we had major equipment running in the ship, like the aircraft lifts, to see if they affected the comfort. And there was 1 day was required for these measurements. Okay, the results: propeller observations and hull pressures. So the objective of this trial was to determine the comparative changes in performance, propeller cavitation, and associated hull pressures with the 4-bladed compared to the original 3-bladed. So the main findings were there was no sheet or root cavitation observed during the run-ups and downs on the forward propeller, and assessed as non-erosive. No sheet cavitation was observed on the afterblades as they passed top dead center. Tip vortex present from 62 RPM and a hub vortex from 74 RPM, and they were assessed as non-erosive. Cloudy dispersed cavitation observed on the suction side route of the aft prop from 168 RPM, and the max pressure pulse amplitudes for the forward and after propellers were within the design acceptance levels. So that was between 2 and 4 kilopascals. The pressure pulse levels for the 4-bladed propellers reduced from 52 and 29% for forward and after props respectively when compared to the original 3-bladed design. So this was a real significant change. In summary, the observations and measurements showed strong correlation with the model test conducted during the 4-bladed propeller design study. The outcome supported and justified the comprehensive methods we used to investigate and remediate the propeller problems. A diver's inspection of the new 4-bladed propellers after 12 months in service found them to be as new condition with no corrosion and no cavitation damage. Okay, now look here. This is a comparison of the hull pressures, right? So this is the port side forward propeller pressure pulse transducer number 1. So the blue line and the blue crosses, this represents what was measured with the original 3-bladed propeller in 2017. The orange ones represent what we measured in March 2021. So that the reduction is significant, and also you can see that the variation about the base frequency, the impulses are much lower, much closer.
What are we measuring along the axis?
Right. Okay. So along the bottom is RPM,
yeah,
and vertical is kilopascals. I was not allowed to show those because maybe sensitive about propeller performance. Okay, and then the small circle here is what Maritime predicted at 100% MCR in the tank. So you can see there's a very close correlation to the design work and the testing, and then the real world. And I think it was a fabulous result, actually. Okay, so this is the prop bore scope observation. So this is to give you first, it's really quite hard to work out what you're looking at if you don't know what you're looking at, which may sound obvious. Okay, so this is the the forward propeller observed from B1. So this is the bore scope most forward of the forward propeller on the port side. So what we're looking at here at the top, so that's the strut, which comes down onto the, sorry, don't want to do that. Go away. This is the after propeller. This is the after propeller blade passing to top dead center. Right, so it's going that way. This is the pod body, and then this is the forward blade approaching top dead center. So remember, it's rotating. This is port propeller, so it's rotating from right to left. Okay, this is the after propeller, looked at from B2 location. Here we can see the after blades passing top dead center. View on the suction face, and a view on the trailing edge of the hub. That's the hub at the back there. You can see it's truncated, and a view of the suction route at the bottom here. And then we got a view of the pressure side route as it approaches top dead center. Okay, that's the orientation. Right, okay, so we're now comparing with 3 and 4 bladed. So this is to see what improvements we had. So this is 2017. Again, this is Canberra propellers. So what we can see here on the 3 bladed, forward propeller at 140 RPM, there's a significant presence of sheet cavitation here, plus a tip vortex. That's the vortex going off there. This is the new 4-bladed, no sheet cavitation, and you can see there's a much finer, much reduced tip vortex. This is a comparison here of the forward propeller at 164 RPM. So again, in 2017, you can see this highly developed cavitation sheet from the blade leading edge, and of course the tip vortex sparring away off the top. Come to 2021, the 4-blade propeller, no sheet cavitation, and all we can see here is a fine tip vortex. And likewise, the after propeller, as you can see, the sunlight's blooming in here in 2017. So the pressure side, leading edge, there's a sheet, erosive cavitation, and down at the bottom, we've got cloudy cavitation on the pan bolts, the securing bolts for the propellers. And then coming on to 2021, and the 4-bladed propeller, pressure side, leading edge, no sheet cavitation whatsoever, and nothing around the roots. So that was a really good correlation what we have between the tank test in Marin's tanks with the new 4-bladed design and the real world. And it shows how much that cavitation was reduced. Okay, summary of the CPAC noise and vibration measurements. I won't go for more, but this is a brief summary. So you can see we did a total of 12 decks, starting from the top to the bottom. There were some issues with noise, which came up, and that's mainly ventilation noise, ongoing problem. But out of all the 448 measurements we took for vibration, they were all within the CPAC limits. And then just to give you some idea of the amount of work that goes into doing the analysis of collection data, data collection and analysis, this is a part of the report. We did one of these for every single measurement, and so what we have, the location of the transducer, in which case it's the center of the compartment. Then we have the CPAC2 limits, so noise in dBs and NR, and then we have the measured noise. Then it was yes or no within limits. And then for the vibrations, we had, so this is peak acceleration 1 to 5 hertz in millimeters per second. In the X, Y, and Zulu directions, the values in faint blue, that's the limits, and the actual measured ones are the ones next to it. And the same again for peak velocity, 5 hertz to 100 hertz, millimeters per second. And again, in the 3 orthogonal directions. And again, everything there was within limits, and very successful. I mean, it was such a huge improvement. And when we went to sea, actually, and we came outside the heads and we got up to about 100 shaft RPM, you could just feel the platform was completely different. It was a normal ship, a remarkable transformation. This gives you some idea. This is the run-ups and run-downs we did. This is for the hospital, which was a very sensitive area. And we can see here that this is a plot of the the different orders. And the fourth order, which was going to be dominant, you can see it's well below the CPAC 2 limit, completely different to what we had before. Overall, through the ship, compared to 2017 levels, the hull plating above the propeller saw a reduction in 60 to 70%. At 5 deck, the main switchboards M1 and M2, which have been vibrating really badly, they had reduced by 41 and 62% respectively. And there's a whole lot there, but the hospital was on 2 deck actually. This was a really good one. This came down by 82% and made it actually a usable space where you might want to be when you're sick. Likewise, the Embark Forces cafeteria, which was another really bad area, we saw a reduction in overall vibration levels there of 68%. And it was just a very good result all round. The only thing was the central mast was fine, but the aftermast is a basket case. It's just the design is going to shake this ship forevermore, so it's going to have to be changed one day. And a couple of cabins right at the very aft part of the ship actually started to vibrate when they didn't before, and that was a 4-bladed induced one, but it was only about 3 cabins. So overall, it was an incredible, successful outcome. And I say the ship staff couldn't believe the change. In fact, the ship was doing MCR, and the navigator came in to speak to him, and he said, "We're doing MCR." So he says, "No, we're not." He says, "We're doing 9 knots." He said, "No." He turned on his screen, MCR, and his cabin was one of the really bad ones. Anyway, just to summarize, okay, the propulsion problems were caused by excessive cavitation and thrust variations with hull pressures higher than normal. We undertook extensive technical investigations to determine the nature and magnitude of the problem. Propeller redesign considered the most effective cost-effective solution. The design study undertaken, which used empirical field data to inform the design and refine model and scale coefficients for tank testing. Extensive modeling, FEA of the shaft completed to provide assurance that the system vibratory response was within operating speed range was acceptable and within class specifications. The 4-bladed propellers have reduced the vibration levels in the platforms to an acceptable level and will not adversely affect the performance of the ship's systems and personnel.